Ladies and gents, let's go ahead and get started here. Let's talk about analyzing rational functions. In particular, this video is going to talk and reinforce what you guys already found out about vertical asymptotes and how those relate to discontinuities of a graph. The end game is going to be talking about how you can graph by hand an accurate picture of a rational function, including all these really important features of a rational function. The reason we're going to do this is because if you can kind of have the discipline and understanding of how to do this for a rational function, your life in pre-calculus and especially in calculus will become much, much easier because these cover basically the other half of the graphs that we could analyze in terms of how they shift around. So we already covered polynomials, just how the a, b's, and c of the parameter change. This is more complicated, which is why it's taking more time, but this is kind of like the rest of the cases. All right. So before we get into it, let's first kind of question ourselves about what vocabulary terms we'll have to know, and especially the important features of them. So when we talk about a rational function, which is kind of like the big deal, the queen of the ball here, we talk about any function whatsoever defined by having division, particularly in the denominator. So 1 over x turns out to be the parent function. Here we have that divided by x. Now that's going to cause some havoc for us later. And I do want you to note that it's going to be having to do with x in the denominator, not just division. So don't get confused in thinking something like this, where we have, let's say, 1/2 x squared plus 2/5 x plus 1/9, which already has a lot of division in it. Even if I throw this over and say divide by 7, that's not a rational function either. So this is what we call like a non-example. This is a non-rational function. This is a rational function. And again, it has to do with not just division, but division by x. When we talk about discontinuities, we're talking about the opposite of a continuity. Now, continuity is defined to be, and probably the best kind of like visual I can give you for the continuity, it's defined to be the kind of graph that you can draw without having to pick up your pencil as you're drawing it. If you ever find yourself picking up your pencil, that means you run into a discontinuous graph. It's discontinuous because there are certain x values that you cannot take in the domain or in the range. Now, these do come in basically 3 different varieties that I want to go through pretty quickly with you here. The first variety of discontinuity type 1, is something we call a jump discontinuity. Okay. Now a jump discontinuity is quite literal, and what that means is that you have this graph and it's going along, going along, going on. All of a sudden it stops, and then it jumps to some other point, and then it continues its journey. Okay. This jump right here in between is the exact thing we're calling that jump discontinuity, is because it literally starts in a different place. This is a weird one, and we'll talk about those a little bit later on. That's not really the focus of this particular discussion, but it's one we're talking about, or at least mentioning because it's a part. The second kind of discontinuity is what we call a limit to infinity discontinuity. Okay. Now, a limit to infinity discontinuity involves typically asymptotes or asymptote behavior. And so let's say we have this asymptote that occurs right here. If you look at the graph that accompanies it, it's probably going to do something like this, where it approaches that asymptote, then has to dive down, or starts from the asymptote and it goes forward. We call this a limit to infinity discontinuity because that's literally where this is going. Like that goes to infinity, and the graph here goes to negative infinity. Now this isn't really like an end behavior type thing, but it's a version of it at least, because it talks about the y value as x approaches, in this case, the asymptote. So that's what we call those limits to infinity. Now this third type, which we will study here in the next coming classes, is something we call removable discontinuity. Now this is really kind of weird. So like the way the removable discontinuity works is that you have this graph that looks perfectly continuous. So perfectly continuous, perfectly continuous, perfectly continuous. And then it takes just like a really brief jump, but it kind of jumps in line. So it doesn't look like a weird continuity, kind of like this first one, where it's an obvious jump. This almost looks like you're just taking away a single value or removing it, and you're moving it up or down. So like the point that we jumped over now appears like above the graph, or in some cases below the graph, which I'm not going to graph that one. And so those are 3 different types of discontinuities we'll encounter. Limit to infinity is what we're concerned with ourselves right now because it has to do with asymptotes. Now, in terms of asymptotes, it does signal a possible discontinuity, or it does signal in some cases end behavior. And so I don't want to make a too big a deal out of this because we already have lots of experience, but I do want to point out that if we're talking about one of these asymptotes or horizontal asymptotes. Like that typically talks about end behavior. And if we talk about a vertical asymptote, okay, that's going to help you find discontinuity. Okay? And that has everything to do with that definition of discontinuity, where it's talking about really breaks, especially the domain. And so if we see the graph that typically goes with this, um, we can see like the horizontal one is going to kind of tell you where that graph's going to end up. The vertical one is going to tell you what you cannot cross. Okay? In terms of end behavior, and I'm just going to sketch another quick graph here. It's important to note, though, when we talk about end behavior, let's just say we have this asymptote. Let's say it crosses at 2. And then we have the graph that goes with it. So let's draw a basic one here. When we talk about end behavior, a couple things to really kind of keep in mind. End behavior always talks about the y value as x goes to infinity or x goes to negative infinity. And we should also always use limit notation when talking about it. And so what I mean is this. If we look at this curve, as this curve continues on until x reaches infinity, it looks like the curve is going to go towards this pink line that occurs at 2. And so the way that we can express that using proper notation is we can say the limit as x goes to infinity of our function f of x reaches a value of 2. Okay? On the other end, we see kind of the same exact thing, except now we're approaching negative infinity. And so we can say the limit as x goes to negative infinity of our function f of x is equal, in this case again, to 2. And so we're using proper limit notation, and we're expressing where the y value goes as x gets very, very big or very, very small. Read that as big negative infinity. Okay? So as we talk about, when we think about rational functions, what should we think about? Well, we talked about a lot of these. This is kind of like a mini summary. We call them rational because the division problem is going to result as a transformation of the parent graph. I'll get to that in a second. But the big thing to consider is that it's going to be a weird graph. Like when you talk about rational functions, it's really hard to say what kind of graph you're going to get. Like you can get pretty skilled at like reading the pieces and eventually get skilled at actually graphing them out. But it's very difficult without a lot of experience just to look at a rational function and have a good sense of what it's going to look like. And so you might end up with something that looks like this, which is probably the most normal type of rational function. You could end up with something that looks like this, which is just really weird, or you could have something that ends up looking like this, okay, which is, again, kind of an unusual looking graph. And so because of this weirdness of the graph, because of the unpredictability that is caused by this division problem, we're going to kind of work these backwards from the way we're typically trained to work problems like this. Let me explain what I mean. And so you don't have to write this down necessarily, just kind of understand what I'm trying to get at. And so if I give you like a polynomial graph, let's say I give you like g of x is equal to, let's say, 2 absolute value of x minus 4 plus 5. The way you'd probably approach this is to try to produce the graph first, and then from the graph try to glean like domain and range, important points, stuff like that. And so like the way I've trained you, and I'm sure you've been trained in the past, is to first look at this, understand like that's up 5. This is going to be plus 4 right, and this is going to be kind of like a times 2 stretch. And so with that information, you're talking about a graphical change. So you kind of start at the parent and analyze the parent to start at 0, 0. And then you start putting in your shiftings. And so this is going to, the minus 4 in there is going to shift it to the right 4. And then you can surmise that now becomes 4 comma 0. And then the plus 5 will move it up 5. And so that will be 4 comma 5. And then it gets a little skinnier, and it's still at 4, 5. And then from here, now you can write your domain and your range, and maybe you find like x-intercepts or whatever, etc., etc. But you do it from basically looking at the graph you produce. Because these graphs are so unpredictable, and it's hard to understand the information by just looking at the graph, we're going to go kind of in the opposite order. And so our kind of operating procedure is going to be to analyze the function first. And in that function analysis, we're going to try to find all that important information. And then from that, we're going to try to sketch the graph. Okay, so this is kind of the thing I want you to kind of get from this is that because of this division, because of this weird behavior, our job is not so much to get the graph right away, but to end up at the graph. And so now the question becomes, well, how do we actually do that? And so does the rational functions graph change in the same manner as the regular polynomials? And the answer to that is no, it does not. It just changes really, really weird. So some things to keep in mind is that it changes because of division. Okay? Um, and that division is going to cause some weird end behavior. It's going to cause some weird asymptotes. Okay. Now I can demonstrate that by bringing Desmos over, and I'll do so just here in 1 second. So if I look at like a function like this, the one I graphed, it's important to know that since that division x plus a, x plus b, you're using that as a division problem, you're just going to end up kind of like with a strange looking graph. Oops. Let me zoom in like this. Okay. And so like when you play around with these parameters, like you just get weird behavior that is somewhat unpredictable. I'm not saying impossible, I'm just saying difficult. But if we have a good sense of what the function is doing, how we can look at the a's and b's and make some determinations, we can probably predict roughly where this graph is going to end up. Not perfectly, but roughly. And so this rational graph does not behave the same. It's because of this stuff, like because of division, because of end behavior, because of these asymptotic behaviors. So now the question is, how can you determine the domain? Well, there's a guiding question here that we have to kind of focus on, and that's what are the roots? Like, what are the roots of this rational function? If we're concerning ourselves with division, then we should concern ourselves with like the division of this problem. So if we, oops, let me get this out of the way. Okay, so if we now need to determine the domain of a rational function, if it's not the parent, because the parent's actually pretty straightforward, what we have to do is consider the roots of the denominator. So, for example, let's say I have this function y equals 2x plus 1 over x plus 4. So the guiding question is we have to ask ourselves is, what are the roots of the denominator? In other words, what makes the denominator equal to 0? So we're talking about this guy right here, the denominator. And so if we want to know what makes x plus 4 equal to 0, we could set up the equation. This one's probably not necessary to know that x is going to equal negative 4. Now, what's really important to note here is that means that the function has to be discontinuous at x equals negative 4 for that value. And in this particular case, it's going to be a vertical asymptote. That's going to be at x equals negative 4. And so what we can predict on the graph is if I look at this graph, at negative 4, we're going to see this vertical asymptote. And so like the graph would maybe come up to that asymptote and then go away from that asymptote. So definitely going to be like a limit to infinity kind of discontinuity. Now coming back to Desmos, we can actually see that. I already have it pre-labeled here to graph. And so we see like we have this graph, this curve just as kind of predicted. Now it's actually upside down from what I predicted, but that's okay. What I was looking for is this asymptote, and that's what I got here. So we have this x equals negative 4 as our asymptotic behavior. Point being, we can't actually reach this value. Okay? So we can come up to negative 4, we can come away from negative 4, but we can't actually reach this x equals negative 4 value. So that becomes like a pretty obvious procedure for us so we can repeat. So even if I make the function a little more complicated, so let's say we have y equals x plus 1 on top, and that's divided by x squared plus 5x plus 6. Our guiding question still stands. What are the roots of the denominator? What makes the denominator equal to 0? Let's focus on this piece here. Now that's a quadratic, so I'm pretty sure I can factor that. If not, I could do completing the square, maybe quadratic formula to find the roots. But here, this should factor into x plus 2, x plus 3, which means my discontinuities are at x equals negative 2 and negative 3. And in this particular case, they turn to be vertical asymptotes at x equals negative 2, x equals negative 3. And so again, if we go to the graph of this, what we expect to see is that at negative 2 and negative 3, we should have these asymptotes. And so our graph might do something kind of like this. Okay? where again we're seeing these two lines, these two vertical asymptotes, we're unable to actually cross them. Okay? Now from this, we should be able to naturally write the domain, because we were looking for domain violations. And so on this one, if we're saying x equals -4 is a discontinuity, that means we can't take it as far as our domain. But our domain can start at negative infinity, go all the way up to -4, rounded bracket because we can't use it, and then start again at -4 and go all the way to infinity. So we can use set notation, interval notation, excuse me, to actually write the domain. Same thing for this guy over here. And so we have a domain that's going to start at negative infinity, go all the way to -3, can't use it, so we use a rounded bracket. Start again at -3, go all the way to -2, round bracket, and then start again at -2 and go to infinity. And so once we have our function analyzed, we don't even really need our graph to know where our domain violations are, so we can go ahead and write our domain absolutely quickly. All right, just a couple of the questions. So why do vertical asymptotes signal a discontinuity in the domain? Well, this is pretty straightforward actually. If we consider the function y equals f of x, and let's just go to the parent 1 over x. Now here we have the discontinuity x equals 0. Well, if we take a 0 and we plug it in for x, we'll end up with 1 over 0. Now this is a problem for us because we can't take something and divide by 0. This is going to be undefined. And that's actually why it violates our domain. What we're actually saying is at these points, at -4, at -3, -2 in the upper problems, or 0 for this one, we'll end up with an undefined division problem. And so we're trying to avoid that. So the numbers you're actually picking out of your domain, that you're removing from the domain with these asymptotes, are the numbers that make the value equal to 0. And so if we think about like f of x equals 2x plus 1 over x plus 4, and you said the domain violation was at -4, well, take f of -4. The top will be 2 times -4 plus 1, and that'll be over -4 plus 4. So in other words, that'll be -7 over 0, and again, that's going to be undefined. And so again, when you're talking about removing numbers from your domain, when you're talking about these vertical asymptotes, this is the chaos that division creates. If you choose numbers that makes the bottom of a fraction equal to 0, you have an undefined fraction, which is actually no good. It makes your function not there, which is why the function literally does not occur at those asymptotes. That's why those lines cut off your function. That's why you have those jump discontinuities. And something we'll explore in more detail later, but this should be good enough for now. So I'm going to leave you with this question, which is, can these discontinuities be eliminated or removed from the function? Can you eliminate the asymptote? And so I'm going to leave this as kind of like a question mark. And so this is something we're going to cover a little bit later, so please leave some space in your notes because we have to come back and actually fill that part in. So now it's time for you guys to write the summary. Now this has not gone well in the past, so I want to give you some advice. If you want to write a good summary, what you actually have to write is something like a movie trailer, not a movie review. Okay? So if you think about like a movie review from like your friends, they're going to tell you whether they thought the movie was good or not. They're going to tell you whether it's worth seeing. They might tell you a couple like nice general ideas, like this is basically what happened. But if you think about like a movie trailer, they tell you a short version of the entire story. In some cases, a movie trailer is more exciting than the movie itself because it only has the most exciting parts in it. And so if you want to write a good summary, you get to think about writing a movie trailer for these notes. And what I mean by that is you should go back to your notes and you should write the shortest version of them that still includes the most important information. Think of it like survival. Like what's the minimum you have to know so you can actually extract these vertical asymptotes? Because I told you a lot of information. Not all of it is 100% necessary to actually getting the vertical asymptotes and finding the domain correctly. And so that's what you got to do for me, all right? So that's my contribution to this video project. I'll post everyone else's soon.